If you're a developer, DevOps engineer, security architect, or technology leader, chances are that in September you had some uncomfortable nights. On September 8, 2025, the NPM ecosystem, which is the foundation of all JavaScript development, was under attack. There was over 500 packages with 2.6 billion downloads that were impacted. We're talking about packages that are used by applications in production. Over the next few days, we saw chaos. There was emergency security meetings being arranged to understand the impact. There was frantic dependency audits being performed to determine what are the packages that are impacted and how deep does that compromise go. And we saw production systems also being halted. The question everyone was asking was, how did this happen? And more importantly, how can we make sure this does not happen in future? Welcome to the Cyber Architect. I'm Cornelius, and in this episode, we are going to be going into the details to answer these questions. We're going to be applying an architectural lens to look at this system, the NPM ecosystem, to understand what are those architectural decisions that made this inevitable, and how do we ensure that software releases processes in future, including the ones that you're currently using, should be designed to prevent similar attacks. Let's be honest, this wasn't some complicated nation-state attack. This was an architectural failure at scale. So let's dive in. Now, before we go into the details, we need to understand what we are dealing with. NPM is a critical infrastructure for the entire JavaScript development. You have e-commerce applications, banking applications, even enterprise SaaS applications that depend on NPM. There's over 17 million developers contributing globally, and over 2 million packages in the registry. And the NPM saves billions of downloads every week. Now, what we want to do in this episode is to understand this from an architectural perspective. We're going to determine and discuss what are the architectural elements that existed in this system prior to the attack. We're going to be looking at what the fix did, and we're then going to be focusing on how do you ensure that you set up your own software release processes and supply chain to ensure that you're preventing this type of attack and being able to detect should this ever happen. So let's go. Now, the first thing we want to discuss is how is the NPM set up? So over here, before I explain the architectural elements, I want to show you just a quick demo how the packages flow into your system. So NPM is a very simple package management system that can be used to install packages from the registry. And what you normally do is on your system, you install a CLI, a command line interface, which is called the NPM command line interface. And with it, I can then install some packages. So here's an example of a package called .env. And what happens when I install this, and I'm going to save it as well, and you can see over here, there's one specific package that has been installed. Very simple. What happens, what you need to notice here is that when you do that, you're actually downloading the code for this library onto your own machine, which means when you're running it in your application, it's going to be running in the context of your application. That's really, really important because it means that whatever your code has access to, these libraries will now be running in the same context as the user that you're running and therefore have the same level of access. So that's in the simplest case, you can see how that demo works. Now, let's switch over to really understand what are the architectural elements that exist in this system. So the first thing that we want to do is to look at the different elements that exist in this ecosystem. So over here, I've drawn a few elements. So there's consumers on the left-hand side, you have the registry, and then you have the producers. What happens, first of all, let's quickly look at how do the packages end up in the registry. So the typical flow is that maintainers, or I'm calling them producers here, but they essentially are running code and they build the software in their own GitHub repo and so on. At some point, they will use an NPM CLI to make an API call into the registry requesting for the particular package to be published. What the NPM system would do at this point, because this is a sensitive operation, the NPM API for the publish endpoint was designed to require authentication. So if a developer tried to publish this package without any authentication material, that would be declined. So effectively what happens is that the developer needs to go to some authentication service first, get authenticated. So when they are making an API call, they will also provide some authentication token into that API call. In the previous design, the registry then would look at that, validate the token, and then write some data into the metadata service, and then also store whatever packages have been uploaded into a file system. Very simple. On the consumer side, because we know, and the way the NPM is designed is that the packages are public. You can think of maybe for an internal repository, you may have some requirements to protect the packages, but for the NPM registry itself, the packages are publicly accessible, which means that from the consumer side, they don't need to authenticate. They can request a package and then retrieve the package. So what would happen similarly on the client side, they'll be running an NPM CLI. And the way the NPM CLI works on the client side is it expects that there's a design which includes a cache. So what the NPM CLI will do firstly is to look at the cache. When the developer is requesting the package, it will look at the cache to determine if that package exists on the cache. If not, then it makes that API call into the registry to first of all retrieve the metadata. You think about the versions that are available for a particular package, and then the location of the packages. And then once that is received, the client receives the files. And then more importantly, once they receive the files, as we saw earlier, the files are received as compressed files. So at some point, the NPM CLI is going to uncompress the files. It will uncompress the files and put them into the location on your actual system. This is really, really important because, again, as I said earlier, you see the packages or the library, the code, the JavaScript code for the library is going to be decompressed on your local machine or on the production machine where the NPM CLI is running, and then it will be placed in whatever location. So that's how the NPM system works. Now, what we then want to understand is, given this design, what are the architectural elements? What are the things that happened in this system to make that attack possible? There's three key elements that we're going to be focusing on. The first one is around authentication. So we want to understand for the publishers, what is the authentication that is being used? Secondly, we're going to be talking about how do you determine, or how does the NPM registry, how was it determining that the requesting developer is allowed to publish whatever content is being requested? And the third piece we're going to be talking about is from a consumer perspective, how do they get to trust the packages that are in the registry, and what are the architectural elements that enable them to be able to establish that trust? So those are the three key elements, and these are the areas where the attack happened. Now, before we go into the details on that, I also want to show you what could happen if I go back to the code that we have. Remember here, in the script that I have, I'm just loading the package, doing some configurations, and the only thing this package does is to help me read the contents of this file, or some other files you can specify in the config. You can specify the location of the files, but it allows me to read the configurations that are specified here, and it places them onto the process environment, so I can therefore access. Now imagine, and this is where the attack happened, imagine that the attacker manages to compromise the maintainer or the developer for the .env package. Imagine what they can do. So here, if we quickly go through here, I mentioned earlier that the package itself comes with all the code. So here is the code for the package, and I've already gone through the code, so I know where I'm going to change. But for the demo purposes, I'm going to just print something on this line. I'm going to print something on this line, but you can imagine a scenario where the attacker has ability to change the functionality of this code and insert any malicious code. So at this point, for example, they can insert some API call which says read all the secrets. So in this case, if you look at this object, it's the one that maintains the secret. So the attacker can get the objects here and then stream them out to an external service. So if I do this, and what we're going to do, what we're going to see is that whenever I load this package, the attack executes. So if I go back to my terminal and run this, within the terminal, I just say node index. And you notice here at this point, sorry, I need to save this. Okay, so you notice on the, if you actually this executed it the first time. So you notice here the attack happens here, or the code that the attacker has injected happens. The key point that we're trying to demonstrate here is that if the upstream package gets compromised, it means that the attacker can inject whatever code in the library, and that code then executes in the context of the user. That's the key point that we want. So now let's focus on this system now to think about the architectural elements. The first part that we've seen is authentication. So we can see that for the publishers, yes, we want to be able to authenticate. So where was the failure in this case? In this case, the failure were 2 points. The first part was, what is the authentication that is being used? And the second part is, once the maintainers or the producers authenticate, how do they use the authentication material? So those are the two key elements. So now, the way this was designed initially was that it was using two-factor authentication, which seems to be going in the right direction. So they used two-factor authentication, but they were using TOTP, which is time-based one-time password. And the problem with that is that it's actually phishable, which means that the attacker can fool or can do social engineering against the target, forcing the target to release the TOTP. And once the attacker has the TOTP and the password, they might then be able to authenticate on behalf of the user. So that's one point. The second part was, once the authentication is done, what are the authentication material and what is the level of access that material has? In this scenario, the maintainers were retrieving or were being given a token that was long-lived. So that's where problem number 2 happened. If the token is long-lived, it means that an attacker could potentially target that token, extract it from the maintainer's machine, and use it in any other environment. The other part that we want to understand there is that once the attacker has that token, what is that they can do with it? In this attack, what we saw was that the attacker was able to reuse that token to run the publish functionality over to override the particular package that they are targeting. The problem being there that in the NPM registry itself, when it receives the authentication token, it wasn't validating the context of that token. It wasn't checking really, where is this token coming from? What are the entitlements? What are the things that should be publishable using this token once that authentication is validated? All the registry was doing is using that token, checking that the token is valid, and then whatever packages are being pushed would be extracted and put into the registry. So that's the fourth element. The other part to understand as well is that from a provenance perspective, so provenance is a property that allows you to trace back where a particular element came from. So what we saw in this attack is that when the registry is validating the token, it's not going back to look at what is the source of that package. Is it really a valid package? Is it coming from a particular approved software pipeline? It was just really just receiving the package, authenticating that, and pushing it into the registry. So those are the key failures that we saw. The other part that is also important, which it's a design feature which is helpful, and this is the idea of maintaining a cache on the client side. It's a fantastic design idea because then it reduces the dependency on the NPM registry itself and reduces the number of API calls that the NPM CLI would make. But the issue was, because you have a cache, and the cache is maintaining the packages that have been downloaded at a particular time. So think about a scenario where now if I identify there's a vulnerability in a particular package, we go upstream in the registry, we update the packages. But then you have the cache on the local machine. So then what happens, every time you run NPM CLI, trying to install, you may actually be thinking you're downloading and using the correct version, but actually it may just be obtaining that package from the cache. So those are the architectural elements that happened in this case. So just to summarize, you have the type of authentication that is being used. How do you ensure that the authentication is not phishable? So that's one issue that was found. The second one was around the token that was being issued once the authentication passed, and that the token was long-lived. So if someone stores it or it's accessible somehow, then the attacker can use that and authenticate on behalf of the user. The third part we've talked about is the provenance. How do you ensure that this package that was produced through a particular pipeline? So all in all, you can see that the fundamental issue is like the trust model that is enforced. On one side, the registry is trusting, once I receive a token, I'm trusting that they're giving me the correct package. On the other side, we can see that the consumers are also trusting that the registry, first of all, is going to give them the correct packages. And secondly, they're making a big assumption around the producers, the security and the intentions of the producers of that software. Now, I'm not suggesting that we take away or we have to solve all those things. In software, in computer science, we rely on the concept of abstraction And this part where you are downloading a package, you're downloading a library, is a core element of that. We cannot write software for every single functionality that we need. There will always be dependencies that we have to make. So the question then becomes, how do we design our systems? How do we ensure that these systems will operate in a way, knowing that the trust model could still require us to trust things that we may not really understand where they're coming from? So that's the key element. Now, before we discuss that, let's also think about the fix. So the first part that was done to fix is to remove the phishable authentication material. So in this case, instead of relying on the TOTP, there was a requirement to use FIDO, right? Which means FIDO is a specification. You can check it out. It's a specification that allowed you to be able to authenticate in a non-phishable way. So the FIDO specification goes into the details on that. I'll provide the link in the description. The second part is, so we've now fixed that phishable part. We've said now the maintainers will have to do FIDO, so therefore they are not going to be subjected to that phishing attack. The second part is, and this is a key architectural element, instead of requiring or allowing the maintainers to be able to publish code from their development environment, you create some isolation between the development environment and the publishing environment. So that when the developers are required to publish, they're going to push code into the publishing environment. And that publishing environment, the only thing it's receiving is code. This allows you to be able to verify and establish the provenance of the code through this isolated publishing environment or workflow before then that gets pushed into the registry. So that's a key architectural element. That separation between the developer and the pipelines or the environment that is pushing code into the registry. The other part now is, the question would then be, quite right, we've isolated the developers. How do I then still ensure that the publishing environment is not going to be subjected to a similar attack? So the way this is done is to establish trust. And there is a trusted publishing specification that has been issued, and the implementation is actually just using that. Essentially, what happens here is that the developers or the maintainers, their role is to be able to go into, let's say, the NPM registry and to go into the publishing environment and establish some level of trust between those. And obviously, this just involves exchanging some shared secrets and then allowing the publishing environment to be able to publish code using, again, another architectural element here, OpenID Connect. OpenID Connect is an authentication standard, again, which allows you to be able to authenticate. And the key element that you achieve by doing that is to be able to say, once the code runs in this pipeline, the pipeline is going to be required to authenticate, and that as part of that authentication, it's going to obtain a short-lived secret. In this case, if the attacker still manages to compromise one part of the system and gets hold of the short-lived secret, the first point is that it's short-lived. It's not going to be a long-lived, so the attack window is going to be reduced. The second part is that in that token itself, you can have additional context. You add additional context around the subject. You can add things like what is a repository that is produced. You can add things around what is the workflow, what is the identity of the workflow service that is producing. This allows you, for example, to prevent an attacker from executing the code from a different pipeline. So those are important attributes that will be added into the token to allow the registry to do additional context validation before the software is allowed. So that's all in all. Those are the key architectural elements that has been established. Again, just to summarize, the first one is ensure strong authentication for the developers. The second piece being isolate the developers from the pipelines that are producing this. The third point is that the pipelines themselves need to be able to authenticate. And then once they authenticate, they're going to be issued with a token, and that token is short-lived. That reduces the attack window. And an additional point is that token also has additional metadata in it that allows the registry to perform additional context validation. So you can see software release and the supply chain is an important element that you need to secure. So if you're a developer or you're a DevOps engineer, you have to be able to understand what are the different elements that exist and how do you enforce this. In this episode, I've explained to you the key elements that you want to have. Developer isolation from the production environment or the pipelines that are creating the packages. You want to ensure that the developers are authenticating strongly. You want to ensure that whatever authentication material is being used is short-lived. And if you do that, in addition to obviously all the CI/CD checks that you do, checking for vulnerabilities, checking for secrets in the code, etc., all that then comes together to ensure that you can establish or you can generate sufficient attestation as part of your pipeline, which then can then be checked in the registry. So even though this is applicable to a public repository, this attack is something that you need to think about even for your own internal repositories, even for your own internal software development pipelines. To summarize, what we saw here was an architectural failure at scale. What this attack reveals is that there was fundamental design flaws in how the software supply chain works. The packages that were compromised was just a symptom. The real vulnerability was the trust model that was used. The fact that users or consumers are trusting that the registry will always provide the right packages, and the fact that the maintainers were being trusted by the registry by simply providing the token. We see that by applying OIDC and the concept of trusted publishing enables to eliminate most of these attacks. Applying phishing resistant MFA is another additional element that has been added to reduce and attack. But as we know, architecture is only as good as its implementation. So in addition to having these architectural elements, ensure that your developers and architects have the responsibility and the understanding to ensure that whatever implementation, the way they configure the CI/CD pipelines is secure. Remember, security isn't about preventing every attack. It's about designing systems where attacks can be prevented as much as possible. Any successful attacks can be contained, they can be detected, and remediation is in place. Now, the new architecture we've seen achieves this through short-lived credentials and contextual validation to ensure that there is cryptographic provenance as well of the packages that are being published in the registry. I hope you enjoyed this episode. If this architectural analysis was valuable to you, hit the subscribe button, write me a comment. Are you still using long-lived tokens in your CI/CD pipelines? It's time to go and fix that. Until next time, ciao.